Okay, okay, great. I was about to say I'm an expert in computer vision, but by no means am I an expert in how to use PowerPoint. So it's great to be here today. My name's Cameron Cooke. I'm an expert in computer vision for manufacturing and operations. I work for Airbus commercial aircraft in Toulouse, France, and I've been there for about 4 years. And today I want to talk to you about how we're using synthetic data to enable the future of computer vision. And I'm going to apologise firstly for the bait and switch with the title into the metaverse. Now I know metaverse, Mark Zuckerberg, all of these things are very popular, very catchy. Originally I was going to have something about the Omniverse, and then I realised that someone else from NVIDIA was also going to be presenting about the Omniverse, so I needed to go and do something different. Now today I want to talk about 4 different things. I want to talk about the context of Airbus, what we do as a company. I want to talk about what is computer vision. I want to talk about some of the challenges we're trying to solve with computer vision before finally doing a quick demonstration of how you can solve a simple problem yourself using freely available open source tools for generating synthetic data. Now, the context of Airbus. Airbus is a huge industrial operation. As a company, we have more than 100,000 employees. Our revenues are in the tens of billions of dollars. We have dozens of factories all over Europe, making all of the different components that need to come together at our final assembly lines in the US, Toulouse, Hamburg, and China. And here on this map, you can see all the different components, where they're made, all of the different parts for our aircraft. Now, this is a very, very complex industrial system, and I love this image because it gives you an idea of the complexity, how, for example, we'll make all of the wings for all of our aircraft are made in Broughton in the UK, and they're shipped to France, US, and China, and Germany. You know, the front of the aircraft's made in France, the back of the aircraft's made in Germany, and, you know, the parts of the tail are made in Spain. So all of these parts need to be transported. And Airbus came up with the solution to, you know, it's the kind of thing that's like, we had this problem, and when you have a problem and you're in the business of manufacturing aircraft, you solve it the only way you know how. Build a big aircraft to put the parts inside and use that to ferry the parts around Europe. So here you can see we've got the front section have been loaded on the aircraft and they're being flown. I think that's Toulouse there. So yeah, we've got 70 of these aircraft flying to 11 different destinations all throughout Europe. Now, building the aircraft is much like an IKEA set, in the sense that you have to get all the parts, you get them out, you sort them around, you've got the tools, and you put it all together. And the place where we put all of the parts together is called a final assembly line, or a FAL. Now, these are huge industrial complexes, which you can see here, and it's really hard to appreciate the scale. I like this photo here because in the front you can see the row of commercial airliners. In front you can see the cars also for scale. And here you can see the factory where we used to build the A380. We're now turning this into a factory to build our best-selling products, the Airbus A320, which is a small commercial aircraft. It's a jetliner. You would have flown on one before. Now, going back to the analogy of an IKEA set, here's what it looks like on the inside of a final assembly line, where you have all the parts coming in. So Airbus A380, A330, a medium-sized aircraft. You've got the wings coming in. All the parts are coming together. They're all being bolted together. Here you can see the whole thing being lifted up. And they're going to join all of these parts together very intricately at different stations to build the final product. So this is a very complex, very intricate, very involved process. And you can imagine the level of degree of complexity here, and making sure that everything is perfect. Because unlike your IKEA set, and I'll be honest, I've built plenty of IKEA sets in the past, and usually for me, there's always some part that's left over, or there's some mysterious rattle. Trust me, when you're building an aircraft, you don't want parts left over, and you don't want mysterious rattles. That's not good. That is not allowed. So Airbus has a huge challenge. I actually presented at Kodiak's in 2019, and when I was presenting then, obviously it was a very different time. This was before COVID. And the challenge that we had then was that our customers, who are airlines, loved our aircraft, and they wanted more of them. They wanted thousands more. And the biggest challenge that we had was manufacturing more aircraft. Now, post-COVID, we actually live in a different world, and there's a lot more focus on climate change. And the challenge we have now is building new, cleaner, greener, more efficient aircraft, which have a lot more complexity in them in the manufacturing process. But we also still have this challenge now. Everyone wants to travel. There's a lot of complexity with airlines, and they also want to buy more aircraft. So we have this huge challenge where over the next 20 years, we need to build tens of thousands of new aircraft, which are a lot more complex, using new techniques. Now I want to pause for a moment and just explain to you computer vision in a few minutes. Now, I'm sure all of you, this is a great conference, a deep tech conference, I'm sure all of you have seen lots of different presentations about computer vision, but I want to take things back really simply and run through this to make sure that we're all on the same level. Computer vision is how computers see and understand the world, much like humans. When we look at this image as a human, we can see many things very, very quickly without really thinking. We can see an aircraft, it's on a taxiway, we can infer it's about to turn onto a runway, we can see there's some grass, there's runway, the runway has the lettering 3 to L, and from that we can infer that's the name of the runway. So very quickly we can identify these different things. We can also understand the different parts of the image, so we can understand there's an aircraft there, there's some grass there, there's the runway there. So computer vision models are very powerful in the sense they can extract huge volumes of data very efficiently from images. Computer vision is so powerful because much like humans, vision is our most powerful sense. We can quickly and efficiently gather huge volumes of information about the world around us. Now, really, in my opinion, the catalyst for computer vision has been two things. Firstly, access to a huge volume of data. Computer vision as a field has been around for about 100 years. Originally, it was called photogrammetry, where mathematical techniques were used to take measurements from photos. But now, with the advent of computers and the access to more and more powerful processes, we can build more and more sophisticated deep learning, machine learning models, which can infer information from photos. So really, it's thanks to our friends NVIDIA, who have brought us incredibly powerful processors that are capable of using huge data sets, like our friends from Stability and their partner Lion AI, where there's huge data sets. We can go away, we can do incredible things using huge amounts of data. Now, deep learning in 30 seconds, or hopefully less. Basically, traditionally with deep learning, what we've done is we've got a labeled data set. So, for example, keeping things super simple, let's say we want to build a classifier to tell the difference between cats and dogs. We might have 100 images which are cats and 100 images which are dogs. And we tell our algorithm, these are cats, these are dogs. It learns from this, and then we're able to predict, okay, for new images, this is a cat, this is a dog. The key thing here is that we've got labels for our data. We know what's a cat, we know what's a dog. We can tell the computer, this is a cat, this is a dog. Now, computer vision at Airbus. At Airbus, we use computer vision in many different areas. My focus is on manufacturing quality, but other people within the company are looking at how we can use computer vision for airline operations, flight data, and documentation. Flight data is a really interesting aspect. In 2021, Airbus, for the very first time, developed a test aircraft where we're able to perform the first autonomous takeoff using computer vision, where cameras on the aircraft are able to guide the aircraft down the runway for a takeoff and then back for landing. Airline operations is where we're trying to put cameras in the aircraft to look outside the aircraft when it's on the ground. This is hugely valuable for airlines because they can look at what's happening around the aircraft and know things like, okay, the fuel truck's arrived, the catering truck's arrived, there's no baggage. There's going to be a delay because the baggage truck hasn't arrived. So this is hugely valuable information for the airline. My focus is on manufacturing. So how can we use computer vision to enhance the manufacturing process, to reduce delays, to reduce wastage, to enhance safety, to make sure that people are in the right place at the right time, and make sure they're not in the wrong place at the wrong time, as well as quality. Now, most of my talk today is about how we're using computer vision to enhance our quality. As I alluded to before, quality for aircraft manufacturing is absolutely sacred, it's absolutely paramount. However, we're going to make a comparison. there's new challenges that we're facing. Our customers, when they order our aircraft, want more and more customization. Many people make the comparison between aircraft manufacturing and car manufacturing. However, when you manufacture a car, you might be manufacturing 10 million cars in a year. We make less than 1,000 aircraft in a year, and each aircraft is different in its own way. No two aircraft are alike. It's a lot more like if you were to order a Rolls-Royce or a Ferrari or something like that, where you've got very demand, you want this engine, and you want this leather, and you want this trim, and you want this paint. Each aircraft is different in its own way. We're also faced by challenges around climate change, where we have to develop aircraft which are more sustainable, which are more fuel efficient, which can use new emerging technologies like electricity or hydrogen to power them. In addition to this, our new aircraft might have new shapes, they might have new materials, and really the only limit to what we can do is what we can make. Airbus always will sell the best aircraft that it can possibly make. So manufacturing really is the limit to what we can do. And often in manufacturing, the limit to what we can do is what we can inspect. So for example, a lot of our manufacturing process at the moment, we're constrained in the sense that after we have assembled something, we want to be able to inspect, a human wants to be able to inspect it to validate that everything is right. So there's constraints in terms of how physically large things could be. If we could use artificial intelligence and robotics and computer vision to help with the inspection process, we could build structures that are much smaller and much lighter, much thinner and much more aerodynamic. Another theme is digital twins. At Airbus, when we manufacture the aircraft, we always know we can do better. There's always more things we can learn. We want to collect information throughout the manufacturing process so that we can understand what we got right and what we didn't get right. So for example, when we've got a robot that's drilling holes in the surface of the aircraft, we drill 100 million holes a year. There's something like, I did the numbers, I'm probably going to get it wrong, but 100 million holes, 1,000 aircraft, it's 100,000 holes per aircraft, probably, I think. Doesn't matter. There's a lot of holes in each aircraft, trust me on this. And the challenge is that as the robot goes around and drills all these holes, the drill bit slowly gets blunt. And when you've got a blunt drill bit, the holes it drills are not perfect. I want perfect holes. I want every hole to be perfect. So the challenge that we have, and the problem we want to solve, is what if we knew how good every single hole in the aircraft was, so that if the drill bit starts getting blunt, we can immediately stop, we can go and change the drill bit, and we can understand trends. Like we might understand that the holes on the left side are better than the right side, and we can try and understand what that is. So really, computer vision and artificial intelligence would give us the ability to marry what's actually happening on the shop floor with what we would like to happen in practice. Now, in terms of challenges, for me, working in computer vision, the dream case I want for inspection, if I want to do automated inspection, is something like the iPhone. I would love to work for Apple, where they've got all of their iPhones coming down some assembly line. Every iPhone is absolutely identical. You can take one image and capture everything you need to on a single image. All of the iPhones are correctly aligned. By doing something like this, you control the lighting, you control the angle of the camera. When you've got a situation like this, it's very, very simple to look for abnormalities. It's very simple to validate that you have what you expect to have. Unfortunately, we don't really have this situation. We have a lot of challenges around the reproducibility and the coverage. So what do I mean by this? And I think it's on the next slide. When we're doing quality inspections at the moment, often we'll have someone crawling through the fuel tank of the aircraft or looking into this, here's the wheel well of an aircraft that's been manufactured with a torch. So people are looking at this maze of pipes trying to validate that everything's okay. And you can imagine this is super complex. So instead of this situation where we've got a production line and things are coming down the production line, we've got this situation where we've got people manually doing inspections. It's hugely complex. We also have situations when we make an aircraft and we deliver it to our customers, we want everything to be perfect. And our customers are very, very demanding. We want the interior of the cabin to be flawless and perfect, and there's hundreds more than 100 different types of defects that we could have on the inside of the cabin. So to solve all of these problems, so we've got all these different types of defects we want to look for inside the cabin, but also when the aircraft is in service, there's things like dents, scratches, lightning strikes. All these things can happen when a truck drives into the aircraft by mistake, or the aircraft gets struck by lightning or a bird. These things naturally happen when the aircraft's flying around. So regular inspections need to be done. So we're looking at how, do we have the potential to use drones autonomously flying around the aircraft to map dents or scratches on the surface of the aircraft. So the message which I want to get out of this is that we can't just go away and build, we can't just go away and build 10,000 models and for each model collect a whole bunch of labeled data and say, this is good, this is bad, this is good, this is bad, here's a dent, here's a scratch, here's a lightning strike. Obviously, this is completely unfeasible. But because we have such a diversity of situations, we are in the situation where we do need to be able to build models which can cope with this huge diversity in scenes and situations, as well as diversity in how we've actually captured data. So at the moment, we've got people on the shop floor with iPads where when they see an issue, they'll take a photo of that. Or maybe, the dream for us is that they've done some work. Someone's gone away, Cameron's on the shop floor, he's gone away and he's installed some piping and he wants to make sure it's okay before he hands it off to the next person. So what if I had a HoloLens or an iPad, or I took a photo and then I received validation on my phone, 30 seconds later saying, green tick, Bing, everything's perfect. You've done a great job. For us, that's the dream. We also have other means of acquiring data. So we've got things like cobots, we've got drones that fly around the aircraft, which we're developing. There's other devices like this thing here, which is in the middle, which can crawl around the surface of the aircraft and get up really close and take imagery. So there's lots of different ways that we can collect data. There's lots of different situations here. There's all the different factories. These are all, each grey box you see there might be like 100 people working on one part of the production line, making one thing that goes from one place to another, to another, to another. And in all of these places, there's different types of defects that could occur that we want to be able to detect using computer vision. So there's a huge diversity. It's simply intractable to be able to go and collect labeled data. We do not have the iPhone production line. We have this maze of piping with this, I'm not sure if you can see it, there's a guy in the background with a torch doing inspection. It's this hugely complex situation with a huge amount of diversity where no two aircraft are the same. So this really brings us to the question of why exactly do we want to do this? Well, there's a huge amount of value to be captured. Firstly, if we could measure, so we could say, okay, what type of defects do we have? How large are they? Where are they? How often are they occurring? If we could collect all of this information at the coalface, then other people who are a heck of a lot smarter than me could do, they could do their root cause analysis, transmachine. I don't even understand any of this stuff. What my job is to focus on transforming the imagery that's coming from the shop floor, the raw data, into something actionable. The metadata saying, hey, there's a defect here, it's this big, it's at this X, Y, Z position. So if we could do all of these things, we could generate a huge amount of value. Firstly, we could identify faults earlier, we could make aircraft faster, we could have happier customers, and most importantly, the people who are making the aircraft themselves would be happier. Imagine this. Before spell check, I can't even imagine what it'd be like. You'd write an email, and then, your boss would say, come back, you'd write an email, send it to a client. And your boss would email back being like, hey, Cameron, there were 17 different spelling mistakes in that email. Maybe you're not set up for this job. Now, with spell check in Google Mail is telling me that there's 17 different spelling mistakes in my email. I fix them before I send them out. I'm much happier. So there's a huge opportunity if we can do this. We really want to be able to join the analog world and the digital world, where the analog world, which you can see on the left, is the world of the shop floor. This is reality. On the right, we have our digital world. We have our digital twin. Airbus has invested huge amounts of money in digitizing all of its factories, building 3D models of all its aircraft, so that we can accurately do modeling. However, the challenge we have is it's very, very, very hard to connect these two things. When I say connect these things, going from what we want to be able to do is we want to be able to go from the real world to the digital world. We want to digitize what's happening on the shop floor. But in order to do that, we actually need to go the other way to generate realistic data from our DMUs, our mock-ups, our digital models. So in order to solve all of these problems, there's a lot of different problems that we need to solve. We need to be able to build AI models for detection, classification, and segmentation for looking at defects. We also need to be able to build other AI computer vision models that can recognize where we are and understand what we're actually looking at. For example, let's say we're in the cockpit of the aircraft and we want to make sure all the buttons are installed in the right place. We need to actually understand where all the buttons should be and what we're looking at and where we are to understand whether or not everything is in the right place. There's other things we might want to do. So, for example, we might want to measure dents. I'm going to talk about this a bit later. So this is something where we might want to take a photo and we might want to be able to estimate the geometry of a dent, like how deep it is. We also want to be able to quantify how robust our algorithms are. We want to have faith and confidence that the algorithms we've built will actually work in practice. So this brings me to synthetic data. And going back to what I said earlier, building a computer vision model is building a computer vision model for classification or semantic segmentation or any of these tasks is easy enough if you have labeled data. We have so many different types of problems that it's simply intractable to label the data. There's other situations where it's impossible to label the data. So, for example, as I mentioned before, we might want to be able to estimate the size or depth of a dent. And to do that, we might need very, very expensive hardware. We need to go away and create lots of dents. That's hugely challenging. So synthetic data is hugely powerful. And I'm sure many of you have seen animated movies and are aware of the powerful realism that can be developed using modern ray tracing techniques. And here's just an example. You can see on the left and right, these are two rendered scenes which are photorealistic. So for us, what we're looking at is trying to build simulated data that's photorealistic. Now, if all of this sounds familiar, it's because the talk which was given this morning by Korea from NVIDIA, where she was talking about the work she's doing and the tools that NVIDIA is providing. This is, for us, we're at the cutting edge, we're at the coalface trying to apply this in industry, and she's providing the tooling that allows you to do this easily. So, going back to what I said, basically we want to be able to develop training data using our 3D models, and then use that to develop training data which can be used to train our models to find defects in the real world. So maybe a quick example. Let's say that we want to locate forklifts on the shop floor. Let's say that we have a problem where people are leaving forklifts in the wrong place at the wrong time, and we want to build an AI system which will detect when the forklift is in the wrong place at the right time. Wrong time. So we've got our 3D model of the forklift, and what we do is we use we go and generate a whole bunch of renderings of different different objects in different positions. And basically the whole idea behind this is that our system learns how to detect forklifts very effectively under all of these different conditions. Now, what's really interesting is that even though some of the images here you can see are very absurd, like, in our factory we're probably not going to have a floating forklift upside down, it does provide a high degree of robustness to our model where no matter what the situation is, if our model can detect a forklift that's upside down, it'll probably work at detecting one in a factory. And through this process of rendering this training data, we also get access to not only the RGB image, which you can see on the left, but the depth image and semantic segmentation images. So we're simultaneously generating both our data as well as the labels that goes along with that data as well. And if you haven't realized, this is a 1-hour talk, which I'm giving in half an hour, which is why I'm going through very quickly. Now, ray tracing in 15 seconds. Ray tracing is a rendering algorithm that's a physical simulation of the real world in terms of generating images. You've got a camera, and you've got a virtual camera, and for each pixel on the camera, you trace a ray, the focal point of the camera, out through a pixel, out into the scene until you hit something. When you hit something, you go and work out what color that thing is. And you do this, and basically the way you do that is you look at how the light would reflect from that surface until it hits the light. So you do this lots and lots of times for each pixel, so it's hugely computationally expensive. Thankfully, this can be done very efficiently using NVIDIA's hardware to generate a very realistic image at the end of it. To come up with convincing-looking images, there's a couple of different ingredients you need. Firstly, you need lighting, let there be light. And fortunately, some very nice people have gone away and collected a whole bunch of what are called environmental maps. So this is basically where they've captured a 360-degree panorama of lights, of a 360-degree panorama view, and then what you can do is you can feed this into your rendering engine and say, hey, you've got all of these different light rays, they're coming in, full around you, and from that you can generate very, very realistic scene. You can have very realistic lighting. And there's hundreds of these available so that when you use these, your simulation can have realistic lighting. You also need meshes and geometry. NVIDIA also provides access to lots of different assets for real-world things you might find in the industrial environment. In the case of Airbus, we have extremely precise 3D models of all of our aircraft, where all the different things like the wiring, the plumbing, the structure of the aircraft are. You also need materials. So basically, this is, you've got different types of materials. Some materials might be shiny, metal, glossy, glass, and these need to be assigned to different objects in the scene. Then finally, you need the rendering engine. Now, the great thing is there's lots of different open source rendering engines. But in particular, I quite like using Blender, which is free and open source. Our friend Tom from Stability, I think, mentioned some of the work they're doing that's working with Blender as well. And as well as that, there's also NVIDIA Omniverse, which also, thankfully for NVIDIA, and that was the subject of Raytracing's talk this morning. Now, basically what NVIDIA Omniverse does is it brings together all of these different components into a structured way so that you can efficiently generate very high fidelity images. This allows us to take 3D descriptions of our scene and then generate realistic rendered images. However, there's lots of exciting future developments. Some of the stuff I've talked through at the moment is still a bit complex. It took me a little while to work out how to use Blender, how to generate the right materials, how to generate the right lighting, how to generate the right 3D models. But there's lots of things on the horizon. And even when I say horizon, probably the thing for me that's been most exciting has been two developments. One is something called a NERF, which is developed by NVIDIA, and the other thing which you also heard about today from Tom from Stability is stable diffusion. So what NERF is NERF from NVIDIA, NERF, which, and there's a release by NVIDIA, basically it's this deep learning algorithm, or it's this algorithm where you can take lots of photos from lots of different angles and build a 3D representation of a scene, just from your cell phone, just taking images. Deep Dream is the ability to generate extremely high fidelity synthetic images, which could then be used as textures, and I think there'll be a lot of developments there in the future. Now, in the last 5 or so minutes, I want to leave you with a case study. So this is a real-world case study for something we did inside Airbus that worked really well. Now, the case study we had was looking for dents on the surface of aircraft. And as I mentioned before, this is something which is quite challenging. At the moment, it's done with someone with a torch who'll be walking around the aircraft and looking. And we're thinking, what would be fantastic is to have a drone that could fly around the aircraft that could have a camera on it. It could fly around, and then what we could do is we could take the video feed from this, post-process it, and then detect the dents. Now, a fun fact. The first time we had some people, the drone people, who went away, and they built their first deep learning model. And the way they did it was to actually get a section of aircraft just like this one you see on the screen, which they found out the back of Airbus somewhere. I'm not kidding. There was like some piece they'd made of an aircraft and it hadn't quite worked out, and it was just sitting there in like a grassy field. And they're like, fantastic. I know what we can do with this. We can go and we can go and dent it. So they went and got this piece of aircraft and they put all of these dents in it. Then they captured all these images with the drone and they annotated all of their images. So they ended up with a situation where they had something like 11 dents. And they came to me and they're like, Cameron, we built this model, it's awesome, it can detect all of the dents, and they're like, this is great, we can't wait to put into production. And I was like, what do you mean all of the dents? And they're like, yeah, it can detect all 11 dents. I was like, okay, but how does it do on your validation set? And they're like, what's the validation set? And you're like, okay, well, we have a problem here. So the joke here, in case some of you missed it, basically, deep learning models are incredibly powerful, and if you just train it to detect 11 different dents, it'll go away and do that just fine. It'll just memorize the location of the dents. And it turns out that this doesn't work it doesn't actually know what a dent is, it just knows where the dents are on this particular thing. So we sat down and I said, okay, what we need to do is to use synthetic data, because it's not cost effective to get sections of aircraft fuselage and put more dents in it. Not cost effective. That piece of aircraft probably cost €1 million or something like that. We probably don't have the budget to get hundreds of them, which are different colors, different lighting, put dents in them. So I said, what we're going to do is we're going to use Blender, which is open source software, and we're going to use a GitHub library called Blender CLI rendering. What we're going to do is we're going to generate some very simple scenes. We're just going to get a flat plane, which is going to represent the surface of the aircraft. We're going to model the drone's camera, so it's going to have the same focal length, same resolution as that. There's a light the drone has to help illuminate the dents, and we're going to model that there. And we're actually going to model a dent, and you can actually see there in the right hand, you can see the orange line dips down a bit. That's a dent that's been modelled into the surface of this material. Then what we're going to do is we're going to programmatically, and this is the beauty of Blender, is that everything can be controlled using code. We're going to programmatically describe the scene, describe the paint of the aircraft, describe its colour, its reflectivity, all of these different components. And then what we're going to do is we're going to render it. So this is a real output image that we got from this system, and while you can't see it, you can infer the presence of the dent, because you can see there's this green laser line that gets scanned onto the aircraft. You can see how that's being bent there by a dent that's just, you can't actually see it, but you just have to believe me, there's a dent roughly in the middle of the image. So the beauty of this being programmatic is that we could go away, get the metadata from this, so you're simultaneously generating both an image as well as the metadata, and you can go away and generate 10,000 images in a few hours, which is great because I hate data annotation, and I've done a lot of data annotation. I know that annotating 10,000 of anything, I've annotated a few hundred images, and that's painful. I would not want to annotate 10,000 images. And in this case, it wasn't even possible to generate 10,000 examples of what dents on aircraft look like. So we went away, generated 10,000 images, and then we can go back and test on that. We could go and train on this data and test on what was on the aircraft and show that this worked perfectly. So now we have something which we know works, we know the conditions it works under, and we're able to take that and deploy that as a commercial product. And on a final note, why computer vision, why synthetic data is so interesting for me. I'm going to try, I know that time's up, I know the screen's red there, so I'm going to try and keep this short and sweet because I know I'm the only thing between you and going home. But last year in India, there was an incident. An elephant got loose and, well, it's a wild elephant, so it's already loose, but basically what happened was it broke through the fence in an airport in India and started wandering around and got onto the runway, and it had to be chased away. Now, Airbus is looking, and as I mentioned before, we developed this system to go on aircraft as a test where we would enable vision on the aircraft to help ensure that the runway is clear. Now, I want you to imagine of all the things when you're thinking, when you're doing a normal test, you're trying to develop a training data set. You'd be like, okay, let's do a training data set. We're going to, put some cars. If you're collecting this data for real, you'd be like, okay, let's put a truck on the runway. Let's put some aircraft on the runway. Let's put, some cars on the runway. It's going to be a little bit tricky to put an elephant on the runway. But that's the beauty of synthetic data, is we can just go away. Anything you can dream of, we can render. And the beauty now is with tools like Stability AI and Stable Diffusion, these images, both, if you hadn't realized, came straight from Stable Diffusion. When I was preparing my talk yesterday, I couldn't find any photos of elephants on Runway, so I just I just used Hugging Face to generate both of these images with the prompt Indian elephant on Runway. So that's the beauty of synthetic data, is if we can imagine it, we can generate the data to train our models on it. Any questions? Yep. Sorry, I didn't quite hear the question. Is that? So we're still, no, it's this drone system that will sell to airlines to look for dents. We're still developing the software for the drone's navigation, but the actual dent detection thing is complete, so it works to our satisfaction now. Yeah, so it's a global shutter camera, so there's no jello. But also, to answer your question, that's the great thing, is we can just go and simulate all of these things. We can go and we don't have to assume that the laser's always straight. We can say, oh, well, if the laser came loose and it tipped like this or tipped like that, and we can show that the model, no matter what would happen, the model would still work, which is the beauty of synthetic data. In terms of how would we build a model, or how would we solve a problem? Now, I was going to say, just a general comment in terms of this is something we haven't done yet, but we have ideas around where for monocular depth, when we're generating this synthetic data, and I'm not sure, maybe we can go back, the way that we here when we generate the image, we also have access to not only the RGB data that's coming out of the renderer, the location of the dent, we also have access to the range map, so how far away this aircraft surface is and the geometry of the dent. So we could go and train, if we had the right model, and obviously models already exist for self-driving, for monocular depth prediction. This is something where we could use this as a training data set to go and train the model, even though in practice, there's probably no real data set for this, for dent detection. We can go and build our own data set. We can get 10,000 images of synthetic dents and then train a model on that. And we've been really impressed internally how well synthetic data has worked. And it's often surprising how well it has worked. And there's been a lot of arguments where you'll have, there's been a lot of happy surprise how well it's worked, even when there's been a domain gap between what's coming out of the renderer and what is actually in the real world. Any more questions? I think that's that. So I'll hand over to our esteemed, am I handing over to you? Oh, okay, sorry.
All right, thank you, Cameron.
Well, thank you so much for listening. Like, it's the second time I've been here, and it's great seeing such enthusiasm, and there's a lot of youth, and I'm really optimistic, and hopefully I can come back in the future at some point.
Open invitation.
Okay, glad to hear it. Okay,
absolutely.
Thanks, you all.
Thanks, Cameron.